This video, we're going to prove Sylow's first theorem. It says that if p is a prime number and p to the alpha divides the order of g is a group, then G has a subgroup of order p to the alpha. Let's talk about exactly what that means. If p to the 7 divides the order of G, well then that implies that p to the 6 divides the order of G, and p to the 5 divides the order of G, all the way down to p divides the order of G. That is, this group G will have a subgroup of order p to the 7, of order p to, another one of order p to the 6, one of p to the 5, all the way down to p. Now, nobody's saying that it won't have a subgroup of p to the 9. If p to the 9 divides the order of the group, then it will have a subgroup of p to the 9. And of course, it will then have a subgroup of p to the 8, and of course, all p to the 7, all the way down to p. If in fact, say p to the 10 does not divide the order of G, we call that our Sylow P subgroup, okay, of order p to the 9, the highest order. If you like watching mathematical proofs, seriously consider subscribing to my channel. That's what we do here. First, a warning, this proof is going to be a little bit long. And even before we get into the proof, we have to prove something about a combination. Suppose that we have p to the alpha times n, choose p to the alpha. By definition, this is p to the alpha m times p to the alpha m minus 1, all the way up to p to the alpha m minus I, all the way to p to the alpha m minus p to the alpha plus 1, all divided by p to the alpha times p to the alpha minus 1, p to the alpha minus I, and eventually down to 1, which I'll write this way, p to the alpha minus p to the alpha plus 1. Now, clearly, this cancels out. So, we have that m. And we can look at this as a product of fractions. I'm just going to group them this way. So I group those. You have p to the alpha m minus 2 over p to the alpha minus 2, all the way down to p to the alpha m minus I over p to the alpha minus I, and eventually the last fraction, p to the alpha m minus p to the alpha plus 1 over p to the alpha minus p to the alpha plus 1. Let's look at this one here. P to the alpha m minus I over p to the alpha minus I. Suppose that I is, say, p to the r, let's call it r1, times l1, where p does not divide l sub I. I didn't mean to say L1, L sub I. Okay, so what we have is p to the alpha m minus p to the r sub I times L sub I, all over p to the alpha minus p to the r sub I times L sub I. Well, in the numerator, we can factor out p to the r sub I. And we'll be left with p to the alpha minus r sub I times m minus L sub I. And in the bottom, we can factor out the same number of factors of p. And we'll be left with p to the alpha minus r sub I minus L sub I. And this cancels out. What we showed is that whatever power of p I can factor out, let me look over here, whatever factor of p that I can factor out from the numerator, I can also factor out from the denominator. Now, I should show one thing, that something about I. What do we know about I? Well, right here, it's p to the alpha m minus p to the alpha minus 1. Okay, that's the highest I. I is less than p to the alpha minus 1, and I is at least 0. It's 0 right here. P to the alpha minus p to the, p to the, p to the alpha times m minus 0, minus 1, minus I, minus p to the I minus 1. So the least I can be is 0, and the most it can be is p to the alpha minus 1. Okay, so that tells me that this can't have a factor of p larger than, not even equal to, p to the alpha. Okay, so they both the numerator here and the denominator, both have the same factor of p to the alpha. So they all cancel out, and this portion right here, so I'm looking at this right now, everything but the m, everything to the right of this, there are no factors of p. Okay, so the only factors of p this will have is the number of factors of p and m. Okay, so suppose p to the n divides m. Let me not use m. P to the r divides m, but p to the r plus 1 does not divide m. That is, the largest power of p that divides m is r. Okay, so this all implies that p to the r will divide everything that I have in red. And that's the highest power of p, because no p's divide these. They all cancel out. So the only thing that's going to divide that long product, the only way p is going to divide that long product is if and only if p divides m. And that's p to the r. P to the r is the largest power of p that divides p to the qm, choose p to the q. But p to the r plus 1 does not. Okay, so now we can actually get into the proof. Okay, so suppose that p to the alpha divides the order of G. Well, what that implies is that the order of G is equal to some power, is p to a power times m. I want to see one thing. Okay, times m. Now, we want to find a subgroup of order p to the alpha, because that's what this theorem is saying. If p to the alpha divides this, then there must be a subgroup of p to the alpha. Well, it seems natural to look at this set. Let M be the set of all subsets. Notice I did not say subgroups. Let script M be the set of all subgroups of G whose orders are all p to the alpha. And we hope that one of these subsets of order p to the alpha is a subgroup. Okay, that's need to catch that one. If I find a subgroup of order p to the alpha, I'm done. So it's really clever to look at this set script M, because it's the set of all subsets of G that have this order. And we're going to, if the theorem is true, then we should be able to find at least one subset of G whose order is p to the alpha, which in fact is a subgroup. Okay, so now let's look at something different. Let M1 and M2 be in script M. I'm gonna find an equivalent relations. Let M1 be in M. We define tilde by little m1, little m1 is related to m2 if m1 is equal to m2 times g. I shouldn't say little m1, sorry. Just not script m1. Okay, so that's how we define this equivalent relation. Or, is it an equivalent relation? Let us check this. Okay, so 1. Is M1 related to itself? And the answer is yes. M1, for some G in the group. If M1 is equal to M2 times some element G in the group G, then we say M1 and M2 are related. Well, M1 is equal to M1 times E, where E is in the group. Oh, I found out that a subgroup of G of order p to the alpha is equal to another subgroup, or a subgroup of order p to the alpha times an element in G. That implies that M1, this and that, those two are subsets, are related. So I satisfied number 1. Number 2, I have to show that if M1 is related to M2, let me just say one last thing. Also, M3 is in script M. If M1 is related to M2, I have to show that M2 is related to M1. Now, let's just look at something silly about the relation. M1 comes first. If M1, if this is related to that set, then what I call this set must equal to the other set times an element in G. Okay, that is, this implies that M1 is equal to M2 times G. But now, if I multiply on the right by G inverse on both sides, this implies that this M1G inverse is equal to MG times GG inverse, associative law, but that's M2 times E. That's in G. Okay, sorry, that is in G, but that equals M2. That implies that M2 is equal to this, is equal to M1 times G inverse. Now, if G is in the group, that implies that G inverse is in the group. So I have that M2, is equal to M1 times an element in the group G. That implies that M2 is related to M1. So I showed that this started off with this, and I showed that it implied that. Okay, now the third one is the transitivity law. Suppose M1 is related to M2, and M2 is related to M3. And G1 and G2 are in G. Well, this tells me that M1 is equal to M2 times G. Okay, which is equal to any old way of writing M2 times G. And I meant to say G1 there. Another way of writing M2 comes from that relation. M2 is the same as M3 times an element in G. So this is M3 times G2, G1, G1, G2 in G. That implies that G1 times G2 is in G, because G is a group and is closed. Oh, wait a minute. M1 is equal to M3 times an element of G. Hence, M1 is related to M3. Tilde is an equivalent relation. So, just a note that Mi is equal to Mj times G for some G in the group. Now, we're going to now look at a special one. Actually, we have to do something first. So, we have these equivalent classes. The union of all these equivalent classes make up the group G. So, suppose that the order of each equivalent class is p to the r plus 1. That would imply that p to the r plus 1 divides the order of m. But the order of m is p to the alpha m choose p to the alpha. That is, p to the r plus 1 divides this, which happens to be, well, the number of subsets of order p to the r. But somewhere we said this is not true. Let me find it. That was what we did before we started the proof. And oops, here it is. I should have said that. I'm pretty sure I did say it, but I didn't write it. P to the r plus 1 does not divide, because the only powers of p that divide this all come from m. The only powers of p that divide this come from m. And I'm saying that p to the r divides m, so p to the r divides this, but p to the r does not divide m. So p to the r cannot divide that. So what we just got was a contradiction. But p to the r plus 1 does not divide p to the alpha m choose p to the alpha. So what are we contradicting? Suppose that the order of each congruence class is p to the r plus 1. Well, that's not true. That's just not true. So there exists an equivalent class whose order is not divisible by p to the r plus 1. Well, the only things that don't divide p to the r plus 1 is powers of p that are less than the power of p is less than r plus 1. Okay, so I don't know what to call this set. Okay, let this class be. Remember, subscript m has subgroups of order p to the q. And we're taking a class. Remember, we have an equivalent relation, and that partitions this set of elements in M into equivalent classes. And they don't have to be the same size. So we have M1, M2, say up to Mn, where p to the r plus 1 no way divides the order of this group. It has one, it has 1, 2, 3, n elements. P to the r plus 1 does not divide n. Now, let me not say let this be 1. Makes it sound like there's only one. Let that be such that let's call it a name. Let's call it T. Such that p to the r plus 1 does not divide the order of T. That is, p to the r plus 1 does not divide the order, does not divide the order of t, which is n. So p to the r plus 1 does not divide m. So now we're gonna make this subgroup. Define H to be the set of all G in the group G such that M1 is related to M1 times G. Now, let's prove that this is a subgroup. Now, how does G get to be in there? If M1 and M1G are related. Sorry, that's ridiculous. They're equal. They're equal. So now, let G1 and G2 be in G. So what we want to show is that G1, G2 are in G. Well, M1. Now, the entry fee to get into H is M1 is equal to M1 times the element in G. The element in G. Sorry, the element in H. So we have that M1 is equal to M1 times G1. But let's say times G2. But at the same time, we know that M1 is equal to M1 G1. So I'm replacing this M1 with M1 G1. That's how G1 got to be, let me say it, it's in H. That's a big error. It's in H. G sub 1 is in H. That means M1, let's talk about G2 first. That means M1 is equal to M1 times G2. But now, M1 is equal to M1G. Let's not forget the G2. Invoke the associative class. So now we have this. M1 is equal to M1 times that. I don't care what that is. If M1 is equal to M1 times an element in G, so this implies that G1, G2 is in H. And there's one little thing I didn't show. This implies that G1, G2 is in H. Okay, I guess that we should show, so I'm going to move this down. We should show that H is not empty. Okay. Since M1 is equal to M1 times E, and E is in G, that implies that E is in H. This is the entry fee to get into H. You take something from G, and if M1 is equal to M1 times that element, then that element is in H. Okay, so this implies that H is not the empty set. So we can talk about elements being in H. Okay, so we got closure. Now, what about inverses? So, let G1 be in H. That implies that M1 is equal to M1 times G. Let's not call it G and G1. Well, this implies that M1 times G inverse is equal to M1 times G inverse. But that implies that this, which is M1G inverse, is equal to M1. I'm going to use the associative law, GG inverse, but that equals M1 times E, which is M1. Oh, M1 times something in G is equal to M1. Okay, since G is in G, I mean if it's in H and H is a subgroup of G, G is in G, that implies that G inverse is in G. So, since G M1 times this element is equal to M1, this element from G, which happens to be G inverse, is in H. So, I started off with G in H, and I ended up with G inverse is in H. This implies that we have inverses. Therefore, H is a subgroup of G. Okay. So now there's the reason that we came up with this subgroup. We were hoping, or at least we should assume, if I said subgroup, I meant subset. This set H right now is just a subset of G. It's only taking some elements of G. Well, I take that back. We just proved that it's a subgroup. So, did I actually formally write that here? So, we now have a subgroup. The immediate question is, what is the order of H? If the order, since H is already a subgroup, if the order of H is P to the Q, we're done. We found the subgroup. We can go home. Now, let's recall an old friend, an old formula. The number of elements in the class of A is equal to the order of G over the order of H. But the number of subsets in our equivalent class is N. Okay, we're saying that that's our equivalent class that has N elements. And that is going to equal to the order of G over the order of H. Well, that implies that the order of G is that product, is N times the order of H. Okay, we are winding down, folks. Okay, recall, made a big deal about this one, that, well, P to the R plus 1 does not divide N. Yeah, that's what I made the big deal about. P to the R plus 1 does not divide N. And P to the R does divide M. Remember, the largest power of P that divided that number N from the very beginning was R. Let us look at that. Suppose P to the R divides M, but the next power of P does not divide M. So that R is the largest power of P that divides M. Okay, so what we can say about this is, this implies that P to the R times P to the alpha does divide P to the alpha times M. I mean, that's pretty clear, because when you do the division, this goes into here one time, and we are saying that P to the R divides M. p to the r goes into m, I don't know, k times, an integer number of times. 1 times k is an integer. So what I just wrote over here is in fact true. But now, p to the r, p to the alpha m, that was the order of g. And we just realized that the order of g is n times the order of h. So let's just say that. This implies that p to the r times p to the q divides n times the order of h. Now, I claim that this implies that p to the alpha is that p to the alpha divides the order of h. Well, we know that p to the r goes into n. So it better be that this goes into the order of h. So we have this. Well, that implies something very important. That implies that p to the alpha is less than or maybe equal to the order of h. So that's a big accomplishment. If I can show that either it's equal to the order of h, or I can show now that it's greater than the order of h, putting these two box statements together would imply that the order of h is exactly p to the alpha. And that's just what we are going to prove. So now let us let h be in capital H. Let an element little h be in H. Well, what does that mean? That implies that m1 times h is equal to m1. And this is true for all h in H. Okay, that's by definition. If you're in H, m1 times h is m1. Okay, now let's suppose this for a moment. Suppose that h is h1, h2, say up to hq. And also suppose that m1 is an element of m1. Now, I claim that the following set, let's call it the set S, which is h1, m1, each of these elements multiplied by m1, h1, m1, h2, m1, all the way up to hq times n1. I claim that S has distinct elements. Okay? Well, let's argue that that's true. Suppose I take two elements from here, hi, m1, and I say it equals to hj times m1. Well, that would imply, because we're in a group, that we have the cancellation law. That implies that, nope, those two elements were exactly the same. Okay, we did not take two different elements and multiply them on the right by m1 and get the same answer. Okay, so this implies, well, let's think about what that means. let's think about what this means. What is the order of S? Well, let's not do that. What is the order of M1H? What is the order of M1H? Well, this is equal to the order of M1, which is P to the Q. Remember, these capital M's, they all came from script M, and script M only contained subsets of G of order P to the Q. So, by definition, the order of M1 must be P to the Q. Now, this set S is contained in M1. It can't be bigger than M1. It is contained in M1. So, this implies that the order of S is less than or equal to the order of M1. But what is the order of S? But the order of S, well, let's see. It has H1M, it has H2M, it has HQM. Oh, it's the order of H. Okay, and the order of M1, as I wrote here, is P to the alpha, not Q. Okay, so now updating this formula, we have the order of S, which is the order of H, is less than or equal to the order of M1. Ooh, that's P to the Q. Let's call that double star. Now, I have P to the alpha is less than the order of H, and now I have P to the alpha is greater than the order of H. Star and double star implies that the order of H is equal to P to the Q. Now, two very important things. H is a subgroup of G. I think that's it. And the order of H is P to the Q. We're done. We are done. We found our subgroup of G. But we also did some more. We did some more. Here's a question for you guys. What else did we do? We did a little bit more than showing that there's a subgroup in G. There's a subgroup in G, and the order of that subgroup is P to the alpha. We did a little bit more. Leave in the comment section what extras we did. As always, if you like watching proofs like this, subscribe to my channel. Please leave a comment. Tell your family and friends and definitely enemies about my channel. See you guys in the next video. Watch and learn. Don't forget to subscribe.